and welcome to the Lloyd's List podcast. I'm Declan Bush and I write about decarbonisation at Lloyd's List. By now, many of you will be busy trying to work out what the IMO's new net zero framework means for you and for the wider green transition. If you don't know what that is, go back and check out our MEPC post-mortem podcast. There are still lots of unknowns, but a big question is whether the final IMO agreement can succeed in pushing shipping from fossil fuels to green e-fuels made from renewable power. This is where you use an electrolyser to split hydrogen from water and combine that so-called green hydrogen with nitrogen to make ammonia, or CO2 to make synthetic methane or methanol. E-fuels are by far the most expensive option, but they're also seen as the best way to decarbonise shipping in the long term. But not by everyone. Today's special guest is Michael Liebreich, the founder of green energy research firm Bloomberg NEF, a world-renowned expert on the net zero transition and host of the Cleaning Up podcast. Michael has long been a critic of overly ambitious claims about what can and can't be done with green hydrogen. He started off by giving me some estimates of what kind of carbon prices would realistically be needed to make green fuels for shipping viable.
Broadly speaking, you've got the cheapest is biomethane, you know this, and that would require today, or for 2030, which is basically by the time you can build anything, something like $130. And then that might drop because things scale and so on. It might drop sort of 2050, $50. So that's like the best that you can do is biomethane. We've got e-methanol currently 760, dropping to 400. We've got ammonia currently 700, maybe dropping to 200. And e-methanol, by the way, when I say e-methanol, I mean that's using biocarbon. If you try and do e-methanol with direct air capture carbon, we're talking about $1,700, maybe dropping to $1,200, $1,300. Those are dollars per ton of CO2. So my gut tells me that if we're going to do this, which is an if, then it's going to be with either biogas or bio removals, and it's going to be about $100 per ton, maybe down to 50 or 75 if we really get serious about it. And all the other stuff is effectively a waste of time. It's just not, you're not wasting time. It's good to examine, good to debate, good to research, good to make friends with other people thinking about it. But fundamentally, it's not going to happen because when things are $400, $700, $1,200, $1,400, the fact is the politics of that is toxic, the economics of that is toxic, and it's just not going to happen.
Michael and I spoke just before the MEPC 83 meeting, which agreed on a complicated fuel standard with an emissions trading system to raise money. That does amount to a kind of carbon levy of something like $10 or $15 per tonne, but that's a far cry from $700 per tonne, and there's still a lot we don't know about how it will work. Why is green hydrogen so expensive? Well, not much of it exists in pure form. It's hard to store, you have to cool it down to minus 253 degrees Celsius. It's hard to transport, it's hard to handle, and you often end up getting far less power out than the power you put in.
Part of the problem is also, when I've been calling in hydrogen for a bit of a reset. And by reset, what I mean is let's get serious about the cost of hydrogen and the experience curve that we're likely to see, because it's not just that it's expensive. You can say, oh, well, $1,700 today. Yes, but look what happened to solar. Look what happened to batteries. And it's all going to... The problem there is that for lots of use cases, or just on the... Never mind the use cases, just on the production side, green hydrogen is about 5 times too expensive. And this is pretty much everywhere in the world, because where you can make it cheaply in the Gulf or in America, you've also got cheap natural gas. So basically, it's 5 times. And, if you start looking at somewhere like, Japan, it's even worse, right? I got this wrong, right? Back in 2020, 2021, I thought we would get very cheap hydrogen, green hydrogen, eventually. Think about the learning curve. You have to go down the learning curve. You have to actually learn. But I thought eventually we will get to the kind of $1.5 per kilo that becomes competitive. So liquid hydrogen in a ship is impossible. It's just never going to happen economically. engineers can do it, but ridiculously expensive. So it's expensive to transport around, it's expensive to store, it's expensive to distribute, and it's expensive to use. So I was very bearish about that side of this, but I did think we'd get cheap hydrogen. Now, I just don't think we're going to get cheap hydrogen because the learning rate applies only to the electrolyser stacks and not to the whole cost stack of hydrogen production. So we've got a cost problem and we've got a learning rate problem, and then we've got a transport, storage, distribution, and usage cost problem. And of all of these thousands of hydrogen projects, almost none will happen. That's the reality. Almost none of the green hydrogen projects will happen. And hopefully what will happen is blue hydrogen for things like fertilizers and petrochemicals, where we really do need to use hydrogen. We'll probably do it from blue or turquoise or one of these kind of colors. Essentially, we'll take natural gas, hopefully capture and sequester the carbon, because that will be much cheaper than green. It's the only way to do those things realistically, and we better do it right. So we better eliminate the fugitive emissions. We better capture all the carbon. But most of this huge bubble will collapse to being just a bunch of blue hydrogen projects for fertilizers and petrochemicals refiners that need hydrogen.
Big claims about green hydrogen decarbonising the economy were based on estimates that could be made for $1, maybe $2 per kilo.
When all of these marvelous Hydrogen Council, Hydrogen Europe, etc., McKinsey, when they came out with these enormous, eye-wateringly big opportunities, the analysis behind that, they were assuming that green hydrogen could be made, that the cost would come down quickly to $1 a kilo, maybe $1.50, maybe $2, euro and a half in Europe. And the reality is, I've just come back from the Gulf, and the reality is that these projects are coming in at $5 and $6 per kilo. So something like 5 times as high as as people wanted, as these people were saying. And the pathway to reduce them is very difficult. It's very challenging because it's so much heavy engineering and so much electricity, etc., etc. And if you say, well, solar will get really cheap, but of course solar is very intermittent. So as soon as you go for dispatchable electricity to drive your electrolyzers, then you've got to firm your electricity and make sure it's 24/7 and so on. So it's just expensive. So you look at these projects, and I hear about them all the time: Oman, Egypt, Saudi Arabia, Morocco, and those are the sort of the most promising from a cost perspective, but they aren't finding off-takers. Nobody's buying the offtake. And the reason is that whoever buys the offtake has to pay that cost delta. Usually there'll be a government grant, taxpayers' money, to do the front-end engineering. And at that point, when they do the front-end engineering, that's where it becomes blindingly obvious that this stuff is really expensive. And then things tend to go one of a couple of ways. Either they disappear, or they very rarely get cancelled. Very often they get delayed. We said it would be 2028, it might be 2032, those sorts of things. But the numbers that actually get to the final investment decision, and those that do, are very small. So there's a lot of things that do 9,000 tons per year, 15,000 tons per year, 90,000 tons per year. But the world uses already 100 million tons per year of hydrogen for fertilizers and in refineries for hydrocracking and making methanol and so on. So when you've got 100 million ton problem and you keep putting out press releases about projects that are small, that are a few tens of thousands of tons and so on, then there's a problem. And these big projects, because the bigger the project, of course, the more important the cost gap is. Now, if you've got a $1 per kilo problem on a 1 million ton project, 1 million tons is 1 billion kilos. So you multiply $1 by 1 billion kilos, that's $1 billion a year problem. Somebody has to come up with that money. And that's not all, because just coming up with that money for 1 year is not good enough. So it's 1 million tons a year. So it's $1 billion problem per year. But actually, to build it, you've got to have probably a 15-year minimum offtake. So Air Products signed a 30-year offtake with NEOM. So let's call it 15. So you've got, for 1 million tons, you've got a $15 billion upfront problem. You need somebody bankable, probably a government, maybe a petrochemicals refiner, maybe a Shell or somebody like that. But somebody has to come up with $15 billion upfront, sign away their balance sheet in order to get 1 million tons a year. And of course, at the moment, the problem isn't $1 per kilo. Right now, the problem is more like a $4 per kilo. So if you want to do 1 million tons with a $4 per kilo problem, then suddenly that becomes a $60 billion upfront commitment from a minister of finance or from a huge corporation or whatever. And so that's the real economics. And meanwhile, Europe is running around with a hydrogen bank and H2 Global, this facility where you can buy hydrogen and import it and from Namibia or Chile or whatever. But those things have got 2 billion euros or 4 billion euros to spend. And 1 million tons, 1% of the global current hydrogen demand will cost something like 60 billions of subsidy up front. So we are absolutely miles from solving the existing hydrogen emissions problem, because that 100 million tons, of course, is fossil. So we got 2.5% of existing emissions driven by hydrogen that's used in fertilizers and refineries. And if you've got a let's be really generous and say that you've got a $3 problem, which would be extremely optimistic. That's $4.5 trillion that somebody has to find in order to solve that problem. That's before you even think about shipping, right? That's the scale of where we are in the whole sort of hydrogen discussion. We have a sort of $3.5 trillion problem, and we're running around with a few billions pretending that we can do not only existing hydrogen, but also aviation and shipping and long duration storage and, hey, taxis and trains and ferries and, oh, why not try and heat people's homes? And I've never seen such a disconnect between the size of the problem and resources that would be required to solve it and the proposed solution.
So if e-fuels aren't a viable solution for shipping, then what is? Michael says we should stop using biogas from industries that are easier to decarbonise, such as land transport and heating homes, and put it into shipping and aviation where it's most needed.
There's a lot we can do to decarbonise the economy that's actually pretty darn simple. We know we can decarbonise the electrical system because we're doing it all over the world. There isn't a country that is getting dirtier in its power system. They're all getting cleaner at different rates. UK is now fully off coal. Even China is essentially at peak emissions now, and likely to be coming down, largely driven by electric vehicles, but also, although they're building coal, they're not using it very much. The capacity utilization is dropping. They're doing so much wind and solar. So every country, electricity goes green. Then we know that we can do land transportation green. Everything from two-wheelers, buses, trains, of course, have been going electric and therefore going green for many, many, many decades. But also last mile delivery, vans, and now, hopefully, with Pragma Charge that I'm working on, HGVs as well. So we do transportation. We do space heating. Maybe most of it will be heat pumps. Some of it might be radiative heaters or whatever, but we can do heating. And then we can do all the low temperature heat in industry, which goes to industrial heat pumps. Anything up to 200 degrees heat and steam, which is fully half of industrial heat, can go electric, and actually probably with either at the same cost or soon cheaper. So why don't we just do that? That is such a big kind of feast that's out there in front of us. And I think that's the direction of travel. We don't necessarily have to do all these very complicated things right now. in due course, no doubt we will have to, but there's so much that we could do right now that, there is part of me that says, how much should we worry? We should certainly not do things that have vast carbon prices.
So, are e-fuels a waste of time, as Michael reckons they are? Dr. Tristan Smith heads the Shipping and Oceans Research Group at the UCL Energy Institute, and he begs to differ.
So your question, are e-fuels a waste of time? So we don't think they are a waste of time because, of course, they're expensive. All of the options to reduce emissions from ships are expensive. The question is, what's the least expensive, very low carbon solution? And when you answer that question, you have to compare the e-fuels, which are expensive, with other solutions that reach the same level of carbon intensity reduction, of which there are certain biofuels able to achieve very deep levels of greenhouse gas emissions intensity reduction. And some of the cost of production for those biofuels would make them comparatively expensive to the e-fuels. So if it was just about cost of production, it's not clear-cut in our analysis that e-fuels would be the answer. But that's where the problem of the total available supply and the scalability of supply of those biofuels becomes really important. And so we've always tried to factor in that there is a genuinely scalable production potential for e-fuels. The only constraints on e-fuels is on the capital available to deploy them and on the space needed.
Tristan says there are enough sunny and windy locations in the world to make e-fuels at scale, assuming you have the money, but there aren't enough of the right kind of biofuels to meet future demand. There'll also be lots of competition for biofuels from other industries, so their price will be pushed up and up.
But when we look at the space availability, there isn't a shortage of space in the world in sufficiently sunny and windy locations. But there are shortages and constraints on the total supply of bioenergy. And to be sustainable, the bioenergy will need to come from waste sources. So it can't be new crops that we're planting in order to harvest energy, because that's then competing with food, it's competing with various land use change consequences, which would then undermine its sustainability. So we're talking about a certain volume of waste products that currently exist from, for example, manure, from wastewater, from crop-based residues, so the waste products left over after harvesting food. Like all of these things can be used to generate bioenergy. And when you sum up the potential, you get to a total supply, which isn't dissimilar to the total demand for shipping's decarbonisation. But it is of a much smaller supply than the total demand we have for a liquid fuel globally. That's across both the shipping sector, but also the other transport modes like aviation and to some extent land transport, but also other processes that will need that biomass, including biomass energy and CCS, including in the plastics industry, where we will need the biomass in order to manufacture plastics in the future, as well as synthesize energy. So there isn't an obvious solution in the bioenergy future to meeting all of shipping's energy demands at cost of production. There is a very likely scenario that this sustainable supply will be tightly competed, and that will drive the price significantly above the cost of production in a way that e-fuels do not face a similar pressure. And therefore, I think we need to be factoring that in as we think about shipping's future, and that's why we've been trying to factor those considerations in.
And speaking of shipping's future, we now have the basic details of a globally binding regulation to price carbon for the first time ever. It won't do much for e-fuels in the near term because the reduction targets are too weak. But Tristan says the IMO can still make e-fuels happen by excluding other options from being considered ZNZ, that's zero or near zero carbon in the IMO jargon. The right combination of strong rewards, surplus units, and penalties under the scheme, he thinks, could just make the difference.
So the key next part of the puzzle for me is the Z&Z reward mechanisms specification. So whilst I recognise that the LCA guidelines will be really important because they'll give us the basic scoring and the certification process for different types of fuels, the puzzle that we didn't solve and that was left ambiguous was that there would be fuels that were rewarded, that they had to have a GFI lower than 19 grams of carbon dioxide equivalent per megajoule, which sets already a threshold where we can say, well, there's only certain types of e-fuel, certain biofuels that have got very low carbon intensity that would be eligible as a minimum. But we will then have a discussion about whether there will be a subset of all the fuels that meet that GFI limit being rewarded, or only some of them meeting that GFI limit being rewarded. And then a further conversation about whether the reward price, the level of compensation given, the subsidy given, is constant or whether it's varied depending on the fuel's production pathway. And so there's quite a spectrum of outcomes that could still arise that could see bio-LNG being rewarded and made as competitive as e-ammonia, or only e-fuels being rewarded and therefore bio-LNG or biomethanol not getting any additional support from the reward mechanism, which will then change the competitiveness and therefore the relative attractiveness of these different molecules. And so it's not an outcome so far that is clear-cut on the definitive answer for the near term, by which I mean the period out to about 2035, as to which of those molecules is going to be the most competitive. In the longer run, I think it is clear-cut. I think that 2040 GFI limit of 65% is going to make it very difficult to be competitive unless you're using ammonia. Whether that's blue ammonia or green ammonia is a question for further consideration, because there's prices and carbon intensities of blue and green that will need to be examined in detail to evaluate that. But that makes the molecule less uncertain in the 2040 period. But the question that isn't resolved is this question about what's the pathway that you would want to be aligned on in order to get to 2040. Can you get all the way to 2040 with a dual fuel ammonia asset from the early 30s competitively, or is there another molecule that is going to be more competitive? And that, I think, gets resolved in the design of the reward mechanism and the Z&Z definition, that, as well as the LCA guidelines, that unfortunately we're going to have to wait for another 12, 18 months, 2 years to see finalised. We also reached the conclusion several years ago that if you wanted to close the price gap to the e-fuels, you would need this $600 or $700 carbon price, which was never going to be politically feasible given the impacts on states that would then create. But the smart thing about the way the IMO's come up with the solution to that problem of how do you close the early adopter business case is that they don't make the entire fleet, they don't penalise the entire global shipping fleet with a very high carbon price to close the business gap. They charge a relatively small price on the global fleet, equivalent to $10 to $15 per tonne across the global fleet as an average, and then use the total revenues that generates as a subsidy of the level of $700 a tonne. I mean, we don't know exactly what the subsidy level will be. It'll be a function of the reward conversation. But it can reach a very high level of equivalent carbon price in the reward mechanism because it's only being returned to a very small percentage of the fleet. Now, the problem with the IMO outcome being a relatively modest levy equivalent to 10 to 15 on a universal levy basis is that there's no credibility that that revenue would meet a scaling up of demand for subsidy. So it meets the initial demand for subsidy for a small 3, 4, 5% demand for subsidy, but it can't meet the demand of a scaled up amount of subsidy. So that's the next part of the puzzle. But even doing it at the small initial level is a tipping point that could be important for the overall transition. And we'll have to see what other mechanisms we can have, including the review mechanisms of the IMO's policy, to then fix the scaling up and achieve as high a scaling up as possible over the subsequent period of the 2030s.
The question we always come back to here at the Lloyd's List podcast: which future fuel should you buy? It's still not clear-cut since the rules are not yet decided, but Tristan Smith predicts ammonia or methane are the two front-runners.
So let's just talk about methane, methanol, and ammonia as three alternative options, alongside, obviously, a conventionally fueled vessel. I don't see any potential for methanol at the moment. There's nothing that looks particularly rewarding. It doesn't work in the long run because it can't be produced with the low carbon intensity of green ammonia, cost competitively to green ammonia. So it's not eligible. It's not clearly eligible in the long run. In the near term, you've got biomethanol or methanol produced from a biomass feedstock, which may be attractive for a short period of time. But if the reward is set as a flat rate to the lowest cost of alternative compliance, it might well not be competitive at all. So there might not be a situation where methanol is competitive to ammonia as a rewarded fuel, and there might also not be a situation where methanol is competitive to a bio oil, like a very low carbon intensity biofuel that could be used in a conventionally fueled ship. And if that's the case, then it doesn't look great for methanol in the short term, in the near term, in the kind of rewarded, subsidized period of the market, which then leaves the question between methane, which has this very, very good opportunity in the very near term. So there's a competitiveness of LNG in a lot of our analysis for the first couple of years, and that's being shown by others as well. But then it becomes less competitive quite quickly. So there's a question about whether or not the reward mechanism will ultimately end up prolonging this short-term period of competitiveness of LNG, which then creates not really a lock-in effect as much as a fundamental question for the sector to answer, which is, does it really want to play with this molecule pathway, which gives it the marginal benefit in a very short period of time? Or does it want to just get on with where it needs to be in the long run, which is also going to be marginally competitive? You know, the spread between the competitiveness of the LNG pathway over that first 7 or 8 years versus the ammonia pathway is not very significant for someone ordering a dual fuel asset, because in both of those assets you can run them on a liquid biofuel, oil equivalent biofuel. You could run the ammonia asset on blue ammonia, which is going to be pegged to the LNG price, so you're covering some of your risk there, and you could run the dual fuel ammonia asset on a green ammonia. So you kind of end up with the optionalities from either an LNG dual fuel or an ammonia dual fuel, which overlap quite significantly. So for me, it's clear cut, because I'm assuming that people will take more than a 5 to 7 year view when they're purchasing the vessel, and I'm assuming that the fuel producers will need a return on investment longer than 5 to 7 years. And on that assumption, I'm assuming therefore that people will end up heading more towards ammonia than they will towards LNG, or aligning their asset portfolio more in that direction.
That's all we've got time for today. Massive thanks to Michael Liebreich and Tristan Smith. For more coverage on decarbonisation, head to the Lloyd's List website, and don't forget to follow us on social media. Thanks for listening. Goodbye.